start. So welcome everybody to
recording in progress.
Welcome everybody to the session number 8 of seminar 1. My name is Peter Tirol from LMU Munich in Germany, and I have the pleasure to chair this session, which will feature 5 exciting talks. And it's a personal pleasure to me to introduce now our chair of the seminar, key organizer, and probably the reason to bring us all together here in this great and exciting conference, Olga Kocharovskaya. And she will present now in the first presentation on resonant excitation of the scandium-45 nuclear isomer transition and its prospects for nuclear clock and other applications. So Olga, glad to share your experience and your exciting news with us. Welcome, and the floor is yours.
Thank you so much, Peter. So in my talk today, I'd like to discuss the possibility to do basically quantum optics with nuclear transitions and X-ray photons. And in particular, recent results on excitation of scandium nuclear isomer with XFL radiation. And what are the prospects for the nuclear clock and other applications based on this? So my talk consists of 3 parts. First of all, I explain briefly the motivation behind using of nuclear instead of atomic resonances. Then I briefly discussed our recent experiment on excitation of scandium-45 nuclear clock isomer, and in the third part, I discuss the prospects for future, the possibility to do super resolution coherent forward nuclear spectroscopy, nuclear clock, and quantum memory. And finally, come to conclusion, hopefully. So, as we know, resonances are in the heart of quantum optics, resonant interaction between atoms, molecules, ion, quantum dots, color center, and so on, with light. And in fact, the best quality factors for the resonance nowadays are achieved in atomic clocks. And currently, the standard of SI unit of time, standard of frequency, is based on hyperfine transition of cesium, about 9 gigahertz. And in fact, it is so high accuracy and stability with this transition that it is SI unit of time, which is based on this frequency, which is in the basis of several other basic units, such as for mass, for current, for length, and for temperature. And nowadays, optical atomic clocks have reached even much higher Q factors and higher stability and accuracy, and it's expected by 2030 that the new standard of time will be based on the optical atomic clock, for example, strontium 87. And it is so good clock that the error within the whole age of the universe is less than 1 second. And the question appears, what is the interest to reach such a good stability and accuracy? And in fact, we know that microwave atomic clocks, for example, enable GPS. And these atomic optical clocks find many new applications. Recently emerged fields of chronometric geodesy, gravimetry, seismology, based on very precise measurements of the gravitational potential of the Earth at a very short distance. And also, it's in the basis of a search for new physics beyond standard model, as it was discussed yesterday by Jun Ye and by Peter Tirol, and in many talks in our seminar, people are doing search for using these atomic clocks for search for dark matter, which is about 25% of the universe. and time dependence of fundamental constants such as fine structure constant, and relativistic gravitational time dilation, and violation of the local invariance and equivalence principle. So there are still many applications, and so even better clocks would be good, but is it possible to outperform these existing optical atomic clocks? Well, here it's worth to have in mind also that such huge Q factors, quality factors of the resonance, have been achieved in atomic transitions for very specific conditions, and it really takes heroic efforts to reach it. It requires high vacuum and is a pull trap for ions or optical lattices for neutral atoms, and cooling to sub-microkelvin temperature. And also the number of atoms which is used is quite limited, just one for ion clocks or up to 10,000 in case of optical lattice clocks. But in principle, a larger number of emitters would be very beneficial, but it would destroy the high-quality resonances, because if you try to unplug these, for example, ions in solids, then as we know very well, that would be many orders of magnitude smaller quality factors. On the other hand, we know that there are nuclear transitions, and for nuclear transitions, high Q factors are quite natural. And what is the most remarkable is that in some cases they can be achieved even at room temperature, and they can be achieved in bulk solids at very high density, so with large number of atoms. And so the question appears where it comes from, all these advantages. Basically, it is based on the fact that these nuclear transitions are much less sensitive to perturbations of electric and magnetic fields. And it's simply due to the small size of the nuclei, about 5 orders of magnitude smaller than the size of the atom. And in stoichiometric crystals, it leads to orders of magnitude low in homogeneous broadening as compared to the optical transitions of impurities in solids, for example. Besides, Mörs-Bauer effect suppresses thermal motion, basically, and so thermal broadening, even at room temperature. And high transition frequency also is very favorable for realization of high Q factors for comparable gamma. I mean, the line width of the transition. So if you look on this graph, which I borrowed from this review paper from Peter Cyril group, you can see that these yellow dots corresponds to the position of the atomic resonances in optical clocks transitions. And these blue dots corresponds to the nuclear transitions. And on the x-axis, we have half-life time of the transition, and on y-axis, we have energy of the transition. And so you can see that all the optical clock transitions are nicely collected around the lifetime of 1 second, from, let's say, millisecond to about 1,000 seconds. And the nuclear transition, and of course, around 1 electron volt energy of the photon energy of the transition. Nuclear transitions, basically, for comparable line widths, you can see that majority of them are around 100 kiloelectron volts or even higher. And so there is only one exception, really unique exception, and it is famous transition. Peter Cyril was our chairman for this session, discussed yesterday and introduced us to this transition, wonderful, remarkable transition around 8.3 electron volt. This transition energy was established very recently in the work of the Peter Cyril group. But However, so far this transition was not yet recently excited. Though remarkable progress was made, and you may have a look on these review papers, hopefully the new one will come because the progress is so fast in this area. On the other hand, there are several transitions which are below about 20 kiloelectron volt energy. And also in the other review paper from the Peter Cyril group, this table shows you these transitions with energy below 20 keV. There are about 10 transitions. And if you look on this table, you can see that actually there is one particularly interesting, promising polarization of the Mös-Bar nuclear clock, which is scandium-45 transition. So let's look for the parameter of this transition. The energy corresponds to, as I mentioned, 12.4 kiloelectron volt, and the lifetime about half of second, corresponding to the line with 1.4 femtoelectron volt, remarkably narrow transition, and the Q factor 10 to 19. However, one should have in mind that predominantly the decay of this transition occurs via the internal conversion. It means that instead of radiation of the photon at 12.4 keV energy, it results in excitation in ejection from the ground state, 1s state of the electron shell of the electron to the continuum, and so the vacancy produced in 1s shell is filled either via the OJ electrons or via emission of the characteristic X-rays, so-called K-alpha, K-beta, lines corresponding to the transition of the electron from 2p and 3p states to the ground states. And so this factor of conversion shows us it's a different value provided in the literature. According to our experiment, it should be this one, which is the yellow colored. And so that the Lamb factor, Lamb-Mös-Bauer factor is also quite high for the room temperature. And it's a stable monoisotope and naturally available as a scandium crystal or metallic scandium. And it's worth to note that this transition was considered as very attractive for Mös-Bauer spectroscopy by Yuri Shvitko and Gennady Smirnov back in 1990. And there were many attempts actually to excite this transition, but by that time, these attempts were not successful because simply no proper source to excite it existed at that time. And so now we're coming to the second part, which is resonant excitation of this transition. And I would like to spend 1 minute to draw your attention that so far there is no actually laser which would be built based on induced emission at the quantum transition as we used for optical lasers. And it was noticed right away in the pioneering paper by Charles Towns that it would be hardly possible to push the concept of optical lasers, what they call so lasers, to the range beyond ultraviolet. And the reason for this is easy to understand. It's because the pumping flux scales like 1 over lambda to the power of 5. So decrease of the wavelengths requires a huge pumping flux. Nevertheless, people succeeded to push soft electron plasma-based lasers up to 5 nanometers nowadays in the group of Jorge Roca at Colorado State University, and also in the group of Shimon Sukever again was demonstrated up to 3 nanometer. And people for a long time dreamed to actually to overcome the problem using instead of ion transition, highly charged ion transition, instead of it using nuclear gamma transitions. And because actually the Mös-Bauer effect was discovered the same year as this pioneering paper was published about lasers. So it stimulated people to look for the possibility to produce the so-called gamma ray laser based on nuclear transitions. It was the first proposal in 1961. And people worked for about 20 years. There were plenty of publications and they were quite enthusiastic, but then it was published this review paper by Baldwin and Solem from Los Alamos and Vitaly Goldansky from Moscow that formulated no-go theorem, gamma ray laser dilemma. So no gamma ray laser is ever possible because pumping which is required would simply destroy the sample. And the problem of gamma ray laser was, by the way, included into the list of 10 fundamental problems by Vitaly Ginzburg in his book. And later, in 20 years, even more, it was again included by him into the new list he formulated in his Nobel lecture. So problem still remains unsolved. And in fact, when we came up with the idea of lasing without inversion, which was based on our previous idea of electromagnetically induced transparency, and very soon similar proposal of lasing without inversion were published by Steve Harris and Marlon Scully group. And the experimental observation of electromagnetically induced transparency was done by Steve Harris, and lasing without inversion very soon, simultaneously in 3 papers and many papers which followed. There was a lot of enthusiasm, and even Baldwin and Solem published a new review where they come to the conclusion that maybe lasing without inversion is the best hope for gamma ray laser. Well, it did not happen, though it allows to resolve the gamma ray laser dilemma. Still, we need sufficiently large gain, and so we need to provide sufficient population in the excited state to overcome of resonant losses. And it turned out that nobody came up with any idea how to realize it so far. So for young people who may be interested, this kind of short review of this problem. And nevertheless, as we know, lasers in hot X-ray range were produced, and they were based actually on the old idea from 70s by John Madej of free electron lasers. And these lasers are very bright nowadays, but they're still very broad. And even in self-seeding regime, when you boost the peak intensity and reduce the line width, it turns out that if you compare this line width, which is about 1 electron volt, with the width of the scandium resonance, which is in 50 electron volt range, you can see that it looks like a search for a needle in a haystack. So it's a very challenging problem. And so that to do this experiment, we used the only laser which provides the proper spectral flux for us, and the only laser which provides sufficient high repetition rate of the pulses, which is also required because the problem even more complicated due to the fact that the position of this resonance of this needle is quite uncertain. So before our experiment, the uncertainty was about 100 electron volt. So plus minus 50 electron volt. And so we had to look for a wide range and we had to scan this laser within this range. And so to make it during the reasonable time, it required high repetition rate laser. And that is the reason we looked for these European XFL facilities. And it provides basically about 10 to the 15 photon per second. But within gamma resonance, of course, you can see that it is 15 orders of magnitude smaller, so 0.7 photon per second. And on a tangent, it was even less. And we were looking actually for the emission of 4 keV photons, which are internal, the photons which are emitted due to the internal conversion process. And so it was very, very small number, about 10 to minus 2 photons per second, but the background was even smaller, and that is what allowed us to observe this resonance. And so this experimental setup, I hope that Ralph will get more time to discuss this experiment. So I'll very briefly just want to mention that what we were looking for, not for the emission of 12 keV photons, which were excited by the XFL, this transition at 12 keV photons and this tangent, but actually we were moving back and forth this tangent and observe the emission of 4 kiloelectron-volt photons, characteristic X-ray emission. And the reason for this, why we did not look directly, well, we looked, but why we actually optimized our experiment for looking for 4 keV photons, because, as I mentioned already, high internal conversion factor, so predominantly decay occurs via internal conversion, and also we expected quite significant line broadening of the transition, and we were right, as I'll show you in a second. But nevertheless, so we were able to detect this resonance. This is a happy team, and I want to emphasize the major contribution to this work, which was done by Yuri Shvitko, which led the project, and by Ralph, which made possible to exact definition, exact measurement of the energy of the transition, and by Jörg, who developed all the data, statistic analysis, and so on. And so this is the resonance which was observed. So this is a normalized counts of the 4 keV photons as a function of the position of the energy of the 12.4 keV photons exciting nuclear transition. And we definitely saw excitation, resonant excitation of this transition. It's a high contrast resonance, about 70% contrast. And the line width of this resonance, of course, is predetermined by the line width of our exciting beam. And the position of resonance was defined with precision about 200 times better than it was known before. And this is actually a very big collaboration, a number of teams involved. And so what's the next? What are the prospects for future? Okay, what it is good for this resonance? How one can use it? The first question appears. So, because if so far all the Mersbar nuclear spectroscopy with excitation by the synchrotron sources, it was built on iron 57 resonance, which is about 5 nanoelectron-volt width. If you compare it with the scandium, it's, you see, 5 million times more narrow transition. And it means, well, maybe it will be broadened, of course, but still it will be definitely a much more narrow resonance as compared to iron. So if it would be just radiatively broadened transitions, then it would be 1 million times better resolution for the nuclear Mersbar spectroscopy. And as we know, Mersbar spectroscopy is widely used for study of quantum many-body interactions in solids and structural symmetry and magnetic interactions and chemical shifts and so on. And in particular, gravitational redshift, which was measured in the famous pioneer and pound Repke experiment mentioned today by Vintilau in his nice talk about gravitational redshift, at the height about 23 meters, and more recently at the height less than 1 millimeter in the group of June year using atomic clocks, it would be available even at a shorter displacement. However, actually, in order to achieve it, we need to observe coherent nuclear scattering. And so far, it was never observed. It was not observed in our experiment. If you look on this data from our experiment, you can see that we were able to detect indeed this characteristic X-ray K alpha and K beta, but we saw only a few photons in the range of 12.4 kiloelectron volts. basically on the same basis as the background photons. And so what was the reason? And what we can learn from this? We can tell immediately that because the background was 50 times smaller than what we observed for 4 keV photons, it means that the number of 12 keV photons was more than 50 times smaller than the number of produced 4 keV photons. And taking into account that the advantage provided by the measuring of the incoherent scattering, these X-ray photons provided us the ratio of expected ratio of the number of 4 keV over 12 keV photons should be about 35. So basically, for 12.4 keV photons, we were about 1.4 times above the background. So basically on the background. Well, for example, if we would just increase twice the length of the medium, because it was the length of the absorber was optimized with respect to 4 keV photons, and we could increase in it twice, it would increase the counting for 12 keV photons 4 times. And it would be fine, it would be perfect, it would be done, we could see this resonance. However, it's not as easy, because one could expect that actually the resonance was strongly broadened. And what does it give? So if you look for the flux of the produced coherent forward scattering photons, it turns out that it scales proportionally to the squared of this optical thickness, but it has this ratio of the radiative line width to the total line width of the resonance. And so if you have any kind of additional resonance, it greatly reduces the counting rates of the 12.4 keV coherent forward scattering photons. And we can see immediately that we have two mechanisms for the line broadening. The first one is a thermal broadening, which is due to the second order Doppler shift, which was first considered by Yuri Kagan in 1965. And it depends on the Debye temperature of the sample. In our case, it is 350 Kelvin, and the temperature, because of the heating of our sample by radiation, was definitely higher than 2 Debye temperature, maybe about it after one bunch of the X-ray photon. So that it means that we had very broadened resonance. It is about 60 times broadened as compared to the radiative line width, at least. And so, in order to have it less broadened than the radiative line width, it would require the cooling up to 35 Kelvin. Okay, I hope it is manageable, we can do it. But we have also inhomogeneous line broadening, apparently. And so we would need to use high quality crystals. So far we use metallic foil. We hope to do the next experiment in scandium oxide crystal. And we are growing, people are growing it for us in 2 places. And so we need to do the nuclear magnetic resonance spectroscopy for those crystals. But what one could expect that inhomogeneous broadening, well, what is typical for these cases is on the order of kilohertz. And people discussed, actually, considering back in 70s, when people were enthusiastic about the gamma ray laser problem, people discussed the possibility to suppress inhomogeneous broadening for gamma transition, because it's not as simple as just, in case of nuclear magnetic resonance, because you have hyperfine structure present both in the excited and the nuclear state. So the standard technique of nuclear magnetic resonance suppression, such as magic angle condition or a specific set, like pure set of the pulses, pi over 2 and pi pulses, would not work directly. But people considered, and we also considered some time ago, the possibility to suppress inhomogeneous broadening at the gamma ray transition, and so perhaps we will need to use one of this kind of technique. So it's not like, hopeless, but it's really very, very challenging, even more challenging than the experiment which was done currently. And also, I'd like to mention that we could hope for realization of the nuclear memory, long-lived nuclear memory as compared to iron-57. And I want just to draw attention to the talk to be given by Shiven, last talk in our session, where nuclear quantum memory was for the first time realized for hot X-ray photons, but switching to scandium would allow, of course, to increase the time for this memory. And finally, nuclear clocks. Well, I'm afraid I'm out of time. Why nobody is trying to stop me? Okay, so I just want to mention
it's so exciting
that actually it is, well, one can expect that they would provide high accuracy and high stability, as it was discussed in this paper from Eckhard Peck and Peter Cyril groups. And also, one could use the advantage of synchronization of nuclear clock with atomic clocks for search for dark matter and other interesting fundamental searches. And one could discuss the prospects for realization of this. It would depend on the realization of the narrow, spectrally narrow, and sufficiently intense source at the hot X-ray range, but I have no time to discuss it. I may answer if you have any questions, if time permits, but I come to the conclusion, and the main one is that this resonance was seen, and in general, these resonances are promising, and quantum nuclear X-ray optics is coming. Thank you. Sorry to be late.
Thank you very much, Olga. This was just an exciting highlight to present it. I think it's worthwhile to invest a few minutes on that to get all the nice story. We probably have time for one question, which is burning from the audience. Just unmute yourself and state a question. Maybe to give Olga the chance to recur to something which she had to jump over. So what would be now, looking back at what you achieved and what you still are working on, what would be the most plausible, most realistic application that you could imagine from this nuclear resonance?
Well, at the moment, what seems to be, the most promising is realization of this coherent forward scattering. Well, actually, it depends strongly what kind of inhomogeneous broadening we have, and it needs to be studied still. But as I mentioned, there are techniques for suppression of this inhomogeneous broadening, and if we could observe this scattering, then it would be immediate application for nuclear spectroscopy, as I mentioned. So it would be much higher resolution which would be achieved, and this is currently the best hope, because in terms of nuclear clock, of course, we are dependent on the sources of X-rays. And so there are passes, and they seems to be feasible, but it's still probably for the future, of course.
Okay. Thank you very much.
Okay, thank you.
I see no more further questions. So in that sense, thanks again. And we move to the next presentation. Staying in the field, now coming to Ralf Holzberger from Jena and DESY, and he will present us about new regimes of nuclear resonance excitation and detection with X-bells. Please, Ralf, go ahead. We cannot hear you at the moment. Ralf, we only see your first.
Yeah, now you should hear me, right?
Now we hear you, but your slide is not yet in full screen.
Yeah. No, yeah.
Perfect. Everything good.
Okay, good. I want to continue actually and try to make up some time so that we don't run too much into overtime. But I will also switch focus a little bit, and I will introduce new regimes of nuclear resonance excitation and detection with X-ray free electron lasers. And Olga gave a perfect example already in the previous talk. I have not much to add to it. So to review this field a little bit, I mean, this nuclear resonance is excited by accelerator-driven sources like synchrotrons, dominantly have a long history since 1985. And here is a chart of the mass power isotopes that have been excited with synchron radiation. These are the blue circles in this diagram where we have the transition energy and the level widths as coordinates. And the symbol size is actually the resonant cross-section proportional to. And so you see the iron-57 is the most popular, most heavily used isotope due to its large cross-section, but not only because iron is a constituent of so many materials in our world that there's a multitude of applications to it. And but also other isotopes are interesting here on this list. I don't want to go through here just the enormously small level width was already discussed by Olga, and here we have the example of iron-57, which is this working horse. But now we have a new kid on the block here. This is scandium-45. So this diagram I have extended. So this is my scandium-45 slide, so to say, here in this talk, to show you actually the orders of magnitude in level width that this isotope is different from the other isotopes. And okay, these are the parameters here again. This remarkably low small natural line widths. And okay, so that is a table with the numerical values. I want to actually emphasize more the applications of nuclear resonant excitations with synchrotron or X-ray laser radiation in many other fields that have been encountered so far. So in the example of iron-57, we have, I want to illustrate how we do mass power spectroscopy with pulse sources of X-rays in general. So the pulse sources of X-rays, due to the short pulse lengths, they are broad in energy. So you are able with a single pulse of this radiation from those sources to excite all these hyperfine split levels at the same time, simultaneously. And this is here the purpose of this animation. So we have a broadband excitation of these levels in this cartoon. In principle, we have the excitation energy distributed over all the atoms in the sample. Of course, we cannot, we don't excite them all at the same time, but we create a state where one excitation is in the sample, but we don't know where it is, at which atom it is. So we have here a set of iron nuclei, sort of, and they are, to repeat this here, they are illuminated by a short pulse, and then within the natural lifetime of the transition re-radiate to actually form a superposition of the wave trains of different frequencies. I've just picked 3 of them here, and the coherent superposition leads to a Moray pattern, which is basically a temporal beat pattern that we record typically as a histogram of the arrival times of single X-ray photons. So that is actually the method, and this is actually a fingerprint of the electronic and magnetic structure of the sample, from which we learn a great deal of properties like internal magnetic fields or electric field gradients that are important for understanding functional materials, nanoscale systems, and so on. So this is has applications in all natural sciences. Here is typical values of the bunch distance and bunch durations at the synchrotron. So we have a prompt excitation, almost delta shaped pulse length that is much shorter than the natural lifetime of the isotope, which is 140 nanoseconds in case of iron-57. So the spacing is about 200 nanoseconds. So in that time we have we can record these arrival times and create these histograms. The important aspect to know here is that at the synchrotron, the photonic density of states, so to say, or the number of photons per mode, I should better say, is well below, far below 1. So at most we have 1 photon at a time in the setup. That allows us, nevertheless, due to the high rep rate of these devices, to record such spectra these days within a few minutes. So by just counting and histogramming single photons according to their arrival time, building up these interference patterns here. So that is the state of the art at a synchrotron. And however, the world does not stand still. The synchrotrons have been further developed, and the X-ray lasers also came up. I mean, this was a transition from a circular orbit to a linear accelerating scheme. And what is plotted here is the evolution of this peak brilliance, the peak number of photons per second per solid angle, per normalized also to the source area and to the spectral bandwidth. That is, it's Moore's law basically in X-ray science that led to eventually to a number of iron-57 resonant photons per pulse that by far exceeds those at synchronous radiation sources if we move from the synchrotrons to the lasers. So we can expect in the case of iron-57 resonance several hundred photons in a single pulse now, and I will show you that we reached this regime, and this will be the core message of my talk today, that this is now possible. And opens up a new field of nuclear resonant science at these facilities. So here is again an evolution diagram of the technology and the same number here over the past decades here that went along actually with technology developments in these accelerators. So and so this leads us to a new regime in X-ray science, nuclear resonant X-ray science, moving from synchronous radiation with at most 1 resonant photon per pulse, creating a single photon excitation that is distributed, delocalized here over this ensemble. And still, I mean, we started the nuclear quantum optics field in this field by using single photon collective effects, because the virtue of this method is that all these nuclei are all identical. We can prepare them very well in the same state that they are basically indistinguishable for an arriving photon that is resonant with the transition. So we were able to observe single photon superradiance, the collective lamp shift. Actually, when we put these ensembles into cavities, I don't have time to review this here, but actually that is what actually the collective effects are doing. They convert this single photon resonance line into a broadened, superradially broadened line that is also shifted by an amount that we call the collective lamp shift, because it's the origin of this effect is based on the multiple exchange of virtual photons in the system. The situation changes quantitatively and qualitatively with LPHYS', self-amplified spontaneous emission radiation that allows gives us several hundred resonant photons per pulse, bringing us into the regime of multi-photon, multi-atom scattering. So we have many identical atoms and we have many identical photons. That is a qualitatively new situation at these sources that gives the perspective on new phenomena. So we can explore photon correlations in a way that has been never explored so far. We can expect nonlinear effects. We can even dream of creating entangled and non-classical states of X-ray light, and have a new look on collective effects that are double collective effects in a way, collectivity in the atomic ensemble and collectivity on the photonic side. So the first goal was to study the multi-photon collective lump shift. The collective energy shift under multi-photon excitation conditions. To put this into perspective, I should mention this experiment that was the very first one about 5 years ago, where the colleagues observed for the first time superradiance of an ensemble of nuclei excited by a free electron laser, where actually the temporal dependence of the emission was studied. That was, this experiment was restricted to the temporal, to the time domain. Nevertheless, it was quite impressive to see the number of photons detected per pulse here reaching up to values above 60 or so. So the spectral component was missing, and that was our goal to tackle. We teamed up with this group here, it's sort of the colleagues from Jena, Hamburg, the DESI group that I'm coordinating is there, and Jörg Evers was the PI with me on this project, and he will talk about this in a different aspect on the next talk. We formed this team, and this is actually a group photo of a part of it, still in the halfway in the Corona regime, so to say. You see this here. Nevertheless, we were quite successful in doing the first nuclear forward scattering experiment at the European X-FEL by forward scattering from a magnetic iron foil, completely of iron 57. That we plugged in here, and this has a magnetization geometry that leads to optical activity, converting the incident sigma polarization, the natural polarization of the beam from the XFEL, where we expected about 150 nuclear resonant photons per pulse, converting this due to optical activity also into a pi component, which we then analyze with the linear polarization filter with two subsequent 90-degree X-ray reflections. So this pi component is solely only due to the nuclear resonant interaction of the radiation with the iron 57. So that is the pure nuclear resonant component that we can filter out with the high purity of 10 to the minus 8 or 10 to the minus 9 selectivity or residual contribution from this sigma. So we have really a high signal to noise ratio of the pi component here. And the first result of nuclear resonance scattering at the European X-FEL was this spectrum here that we then that shows the time evolution up to a few hundred nanoseconds that we then could fit with our theory in a relatively simple way, but it was remarkable to realize that this fit was possible and was really uniquely fitting the experimental data by assuming only 1 micron thick iron 57 foil. So the scattering process is strongly dependent on the thickness. We have a high sensitivity on the thickness, so we would have expected such a resonant time beating pattern. Instead, we observed this one here, that is the same range here, that is completely different from what we expected. So there's this large discrepancy. That is a puzzling effect that we observed. It still puzzles us. We have not yet resolved this discrepancy. This is what we are working on. However, it is an experiment that actually proceeded under this excitation condition. However, yeah, one has to say that the polarization filter was suboptimal. Sorry, I should, this did not perform as expected, so the efficiency was 3 orders of magnitude less. So this polarization filter ensured to some degree that we were still in the single photon detection regime. But nevertheless, we have multi-photon excitation, single photon detection under those conditions that we already discovered this apparent discrepancy. So this experiment we then repeated with an improved polarization filter 1 year later, and this is the new setup here and the new results that I can show you. So finally, we improved the polarization analyzer quality. We also improved the X-ray optical setting, and we used a thin film cavity sample here for reasons. This is the sample actually to where a large collective lump shift was expected. But first of all, we had a polarization analyzer with that performed as expected, and we really could, for the first time, then record multi-photon events. These are the detector traces here with photons, with several hundred photons. Here's an example shown for 300 photons. We went up to 600 photons per pulse. These are single pulse detector traces that we could record here. So the colored line are colored curves here are the signals from the individual APDs, avalanche photodiodes from the stack here. So this is an evidence that we have the possibility now to record these temporal beat patterns on a single shot basis with sufficiently many photons to analyze the fingerprint here and to deduce information about the sample that we have illuminated. So that is actually the perspective actually that is now on the horizon or far above the horizon. Jörg will also certainly tell more about it. Now we could go ahead and tackle the original goal of our experiment, namely the measurement and detection of the multi-photon collective lump shift. So we put in an Doppler drive here with the iron 57 single line energy analyzer, and we were then able to record in a typical Mössbauer manner by recording the events, the detected photons, as a function of the Doppler velocity of this this foil here, and as a function of time after excitation to arrive at this two-dimensional graph that contains the spectral information and the temporal information here in an event-based detection scheme. And we are currently comparing this with our theoretical expectations. So there is a shift in this pattern here that maybe qualitatively matches with what we expect here. Data evaluation is still in progress. I cannot give any final results here, but we have shown that this type of experiment is possible at a free electron laser, and we actually were able to open a new research field for Mössbauer science with X-ray free electron lasers. So that is actually my final slide. I hope I could show you that there are bright perspectives for nuclear quantum optics after having done a lot of work at synchrotrons before we have arrived at X-ray lasers. So this was the summary of what we did at synchrotron so far. I cannot, I mentioned a few of them here. There are other applications using cavities as platforms to to tackle quantum optical phenomena like those I mentioned here. But okay, the outlook here is now to go for multi-photon interaction of nuclear ensemble with X-rays. I mentioned those aspects already. Another new aspect here would be quantum imaging by putting the idea of Hamilton and LPHYS into realization using nuclear events. But this would be a completely different talk. That is a new world coming up at X-ray lasers. And with this, I want to conclude here and thank you for your attention.
Yeah, thank you very much, Ralph, for sharing these really exciting and bright and absolutely fascinating new insights. We have time for questions. Yes, please.
Yeah, thanks, Ralph, very much for this very interesting talk with the most recent results just from May. I would like to know, I mean, you were talking about last year's measurement with the discrepancy between 8 micrometer thick iron foil and the 1 micrometer, which fitted best. And so you were saying you repeated this measurement this year. And could you resolve, by improving the polarimeter or other aspects, could you resolve this discrepancy, or is it still holding?
That's a very good question. The observation is still holding. When we still observe a large discrepancy between the apparent thickness as it appears in the scattering data and the geometrical thickness that we measure on our sample. So this is a systematic behavior that must have to do something with the enormous impulsive load of the incoming photon pulse that leads to maybe some working hypothesis is that is some initial phase scrambling of the emitters, which then in parts leads to destructive interference that makes the thickness appearing much smaller than it is really in reality.
Okay, so you see exactly the same effect. You repeat the same more or less conditions. I
would not say exactly, but it depends on the pulse energy. It depends on the history of how many pulses were there before.
Okay.
So there are many aspects that we are still working on.
Okay, thanks.
Yeah, I see no. Yeah, there is another question, please.
May I ask you just a general question concerning the collective lamp shift? This is, in fact, just a shift of polariton in the extended sample compared to the resonance of the one nuclei or atom. But what can you expect with just 100 photons in the crystal? The multi-photon collective lamp shift could be additional shift, could be only due to nonlinearity. And what kind of nonlinearity you expect with just 100 photons?
Yeah, that's a very good question. And this is, I have to say, totally unexplored, also theory-wise, what happens under such excitation conditions. That's what we are still working on. We have the situation that we have more than one excitation in the system. Of course, there are many atoms, many resonant atoms, certainly much more than we have nuclei in the sample. But what is important, what happens in the coherence volume actually? And the question is then, does the optical properties, does the index of refraction depend on the number of excitations in the system? The effect might be small, but maybe we can probe some effects like this. That would be an indication of, say, a first nonlinearity in the system.
Yes, I agree it's very challenging to see this such kind of effect, but who knows? Okay, thank you.
Yeah.
Yeah, okay. I think with that, we have to move on in the program. Thanks, Ralph, again for his talk and for the discussion. And we come to the next presentation in our program, which is given now by Jörg Evers from MPI Heidelberg on nuclear quantum optics beyond the linear regime, recent progress in theory and experiment. Please. Sound is not yet there.
Oh, can you hear me now?
Now we hear you very well.
I'm sorry. Yeah, then I start again. Yeah, thank you very much. I'm very grateful for the opportunity to speak here and to continue this sort of series of talks by Olga and Ralf on this new progress of nuclear quantum optics. And I want to address some of the questions that came already up as maybe the new ingredient. And I also want to maybe put my point of view, what may be a motivation for this field, which is then also in this framework of the laser physics conference that, of course, we witnessed this tremendous progress, maybe over the last few 200 years or so, from experiments where, in essence, some chemical substances were put in some sense in an uncontrolled way in a flame to excite it, and then it was just passive spectroscopy. And if you observe this description that Ralf mentioned of the synchrotron experiments of nuclei, I have to say that this always reminds me a bit of these experiments, because you go to the sort of strongest sources that you have and just in some uncontrolled way, in some sense, excite it and then just see what comes out of it. And if you see that now at visible frequency ranges, for example, a tremendous progress also driven by light source development has undergone, so that we now have at some point full quantum control, or at least over simple systems. Of course, the question then comes up, if you think about X-ray science, whether something similar can be done there as well. And that is sort of a long-term motivating question for me. So I want to know whether now, if you go to X-rays and you maybe address inner core electrons or nuclei, whether you can maybe also go more to this quantum nonlinear control aspects that are well developed at visible frequencies. And due to these new light sources that we have been hearing about already, clearly now is the right time to do this. And in general, you would, of course, get new tools in X-ray physics, but on the other hand, maybe also a new platform for quantum dynamics. Ralf mentioned this ideal two-level systems you can easily realize. And so I think both sides could strongly benefit from such developments. Now, when you do this, you have to, in essence, decide if you want to go for electronic resonances or nuclear resonances. The key difference is that typically the electronic resonances are rather broad on the electron volt level. So they have a very short lifetime, but it's sort of easy to drive them strongly because you can put a lot of photons in them with the pulse sources. The nuclear resonances are in some sense complementary because they have a very long lifetime and short line width, as we have small line width, as we have already heard. But then again, it's difficult to drive them strongly. And so we decided mostly for the nuclear resonances. And one of the reasons for this is, of course, what Ralf also already mentioned, is that they are really used as a very versatile tool across the natural sciences to gain information about the environment, chemical, magnetic states, spin structure, relaxation phenomena, lots of application. And so the question is, if you now think about this progress at visible light frequencies, whether it would be possible maybe to develop some more advanced mass power spectroscopy than just linear absorption spectroscopy, or apply some quantum optic tricks, maybe even with novel experimental approaches, and thereby get some improvement in the field. And so now, of course, what we are talking about today mostly is this progress offered by the X-ray free electron lasers. And the key advantage there, of course, is that you have this high resonance spectral flux. And depending on what you do, it's the peak flux or the average flux. So you ask, how many resonant photons per pulse for the nuclear, how many resonant photons do you have either per pulse or per second? And depending on this, there are different direction you can go. And it's these extreme isotopes that Olga mentioned that you can drive with a high average flux rate. Then if you have the high peak rate, so many photons resonant in a single pulse, you can think about this multi-excitation dynamics, maybe go beyond the linear regime, where there might be the novel observables that Ralf mentioned. And I think that also the single shot spectroscopy that was already mentioned is really a very important thing, because in essence allows you to do mass power spectroscopy of out of equilibrium phenomena or transient phenomena, which are non-repetitive, because you can just get a snapshot with one go. And that's, of course, in particular interesting if you have some impulsive stimuli, which can be something else. It doesn't have to be X-rays. And so I think this is really a new field which will gain traction soon. And for sure, there will be also other things that we are not thinking about at the moment. So I have this one slide also on the scandium, like Ralf. I mean, the new aspect that I can maybe add is that there's this way that we had to overcome to get this very low count rate and to suppress all the background counts. And that is shown in this animation that we had the incident X-rays coming. And when they hit the sample, which is this small thing going back and down, there's of course a lot of electronic scattering going on, and that was shielded away. And then when the pulse was over, the sample was actually moved between the two detectors here, and only then the gating was on and the detectors detected the fluorescence, and then it was moved back and the next pulse came. And this really shows you this idea that Ralf mentioned, that the excitation is stored for a long time in the solid state target so that you can manipulate it and thereby also direct where the light goes. And that was sort of the key step, how we could implement this seemingly simple setup here. And of course, we hope that now new applications will come up in precision spectroscopy, extreme metrology, and so on, as Olga mentioned it. So this is about the average flux. But of course, the question now comes when you have this high peak flux. And that is also what Olga already mentioned, whether we can now go actually beyond the linear excitation regime. And that is really terra incognita, I would say. And that, of course, is also related to this history that Olga mentioned, that, of course, there are these challenges that have been pointed out a long time ago, for example, related to the gamma ray laser, that is maybe very hard to strongly excite the nuclei. But nevertheless, of course, people have been still trying. We have also tried, I mean, like, for example, this approach to use strong optical or also X-ray fields with accelerated nuclei, and it doesn't have to be Mössbauer nuclei. There's also this hope about target design to improve the excitation, and I will talk about it a bit later on. And there are also new ideas like here by Ventigliao and Adriana Palfi, to also in some sense have a target design. It's a tapered waveguide which you can drive using X-rays and thereby gain at least transient inversion of nuclei in these waveguides. And I think there are many ways proposed. And of course, it's interesting to see then in the future whether some of this can actually be implemented in the experiment. So this first step in this direction was already mentioned by Ralf, this Sackler experiment. What I would like to add is that actually, even though the measurements are, of course, very beautiful, in the end, the authors came to the conclusion that the results can actually be explained with sort of single photon response together with the statistics of independent photon emission. And this goes in the direction of the question on the last talk, that, of course, we have to do more in order to be able to claim or to go in a regime where we might think about some nonlinearity. And it's actually a question if we can reach this at all. And with this experiment that we recently did, that Ralf already mentioned, at least I personally also connected this hope that we could maybe gain some insight on what platforms might be available to go in this direction, and whether we can learn something in this experiment already about limitations or possibilities, and maybe connect also to some previous theory work. And of course, we have some nice results. I mean, like the one thing that I pointed out already, Ralf also showed, is this evidence for single shot spectroscopy, where really, I believe, we have not analyzed it in much detail, that now with this, we can actually really get the structure that we probe with a single shot. And even though it was a stationary one now, of course, it's sort of clear that if we could repeat this with a dynamically controlled sample, one would then, with this, maybe get information about the transient state of the target. And this would, of course, open an entirely new field or new research perspective that one could address with Mössbauer nuclei. So now, but if we want to go further, we have to understand what the effect of the intense X-ray beam is actually on the sample. And I want to talk about this in a sort of different perspective of this 2D spectra that Ralf already showed. And then I want to go ahead a bit in the theory to ask if it's actually possible to enhance the nuclear excitation fraction. And I will talk a bit about focusing X-rays on the cavity, which we didn't do in the present experiment. And then the final question is, of course, also, if we hope that we might have it, how can we actually verify the presence of physics beyond, let's say, multiple independent single photon scattering? And I would like to put up two actually quite simple schemes, which might be practically feasible in my view. So to analyze the stability, we actually can use a scheme that we put forward some years ago. In this paper, actually, we looked about the coherent control of nuclear dynamics, but as one aspect, we use this energy time domain spectroscopy that Ralph already introduced to measure the stability of our control scheme, actually using the Allen deviation of the light scattered by our absorber. And by this, we could really see how stable the control, which is in essence the relative distance of these two targets, on nuclear wavelength scales is as a function of the sampling time. And we could show here that really we could control the motion to well, fractions of the X-ray period if you convert it into a time. And now what we can do is that we can use this technique to analyze the stability also to the data under this higher heat load and the stronger excitation case that we have now at this XFEL experiment. And that is actually quite interesting because we can now compare the two cases of a transmission geometry where we have a foil target, where Ralph, for example, mentioned this current discrepancy that the apparent foil thickness that we see in the data diverges from the thickness that the sample actually has physically. And we can compare it also with the reflection geometry. And to this end, we also analyzed the pulse structure of the XFEL a bit more in detail. So what happens there is that with a 10 Hertz repetition rate, you always get a train of pulses. And I've shown such a train here. And in this train, there are now 30 X-ray flashes. And each X-ray flash excites the nuclei, and we measure afterwards. And then, of course, you could think that you might have early flushes where, for example, the temperature of the sample is still low, and then eventually it will heat up over the train, so that maybe later in the train, the data could be different. And so we analyzed these 2D spectra actually at the beginning, at the end, and averaged over the entire train. And what you can see here is that actually in the transmission geometry, first of all, the interference contrast is not very good. If we just go to very early pulse IDs, you see two resonance structures here, but they are really not clearly resolved. If we go over all pulses, it's sort of blurry. And if we go to the latest one, the interference is mostly washed out. And what is also interesting is that the entire part which remains from the resonance seems to be shifted to higher energies. And so clearly something is going on here. It could be actually radiation pressure pushing the target to the front, or maybe some heating effect inducing some motion. And in this theory model that we set up that Ralph mentioned, these effects can actually be shown to lead to an apparent smaller thickness. So maybe this is actually data that will help us to explain really this discrepancy in the thickness. But of course, we need to analyze it further. But what is now very interesting is that if you go to the cavities in sort of similar conditions, so you just replace the target, you see that actually in all cases, so averaged over all pulses in the train, the early pulses or the late pulses, the interference is similar and preserved. I mean, the count statistic is, of course, a bit different because in all pulses, we just have more signal, but the structures are the same. And so the conclusion, therefore, is expected or unexpected, I don't know, that the cavity target actually appeared to be much more stable under intense X-ray excitation. And so I believe actually, and that was also in the theory a bit hoped before, that they may be actually more promising candidates for stronger excitation conditions because they may be more stable against these intense X-ray excitation conditions. And so then, of course, we can ask, how can we increase the nuclear excitation fraction? And of course, the ideas are fairly simple. You could ask, maybe we can just focus the X-rays because there are many effects, two effects mainly. The one thing is that if you focus the X-rays, then you concentrate the same number of photons on a smaller nuclear ensemble. And so you may hope to excite this ensemble to a higher fraction. Yeah. But the cavity, of course, if we optimize it, can also maybe enhance the field intensity of the free space field. And we have some results which shows this in principle, but at least to the best of my knowledge, this has not really been analyzed using focused X-rays in the cavity. And we actually had some preliminary work here, not considering the focusing, and the results you get are quite different. And so what we did now in a more comprehensive treatment is that we really treated the propagation of a focused Gaussian beam through this planar waveguide, and we have the cavity filled with nuclei and analyzed what happens. And I just want to share you a few results on this, which are actually quite interesting, because what we now show here is actually the field distribution under XFEL excitation in such cavities with different focusing conditions. And so we just use the standard cavity where here the electronic reflection curve is shown as a function of the incidence angle, and you have certain resonances. And now depending On the focusing, you of course have a different divergence of the beam, and thereby you drive a different width of the cavity in terms of the incidence angle. And the three widths that I have considered here in this data are shown by the shading here in the beginning. And in the plots below, you see then the field distribution of the pulse, and in the one direction we have the depth of the cavity, where the X-ray comes from the bottom in these plots. It's measured in nanometers. And on the other direction, we have the propagation along the cavity surface in micrometer. And the pulse is arranged in such a way that in free space, it would just focus on the red dot here. And what you see is that at moderate focusing, you really have this cavity enhancement that you expect. So you have the standing wave going through, and I mean, it's a bit displaced due to the cavity propagation, but you have a strong enhancement of the field intensity. But if you now focus further on, you see that actually the structure behaves in a very unintuitive way. At the end, you do not really have, you actually have less intensity in the cavity than you would have in free space, and the intensity concentrates outside. And there are interesting effects. So you do not have the standing wave anymore, because actually the divergence gets so large that the light hopping back and forth doesn't overlap anymore in space, and so no constructive interference builds up. So that is, of course, not good, because then it means we cannot maybe use the cavity to enhance this. But we have started optimizing the cavity. And so here's the similar conditions where we now choose somewhat computationally optimized a cavity for 40 nanometers, for example. And then you can see that you can actually get the large intensity that you want to have at the position of the nuclei back here. But it also shows that if you optimize for this focusing, that if you go to even higher focusing, again, you have maybe a problem, because you still have a hotspot in the cavity, but it's not at the position of the nuclei. And so really, if you want to go this route, we believe it works. And we have some initial calculation that even with FEL parameters, if we manage to get this high focusing, it may be possible to go in the strong excitation regime. But you really need a dedicated cavity optimization, including the focusing and the full beam properties to get this going. But it seems to be feasible. So then, of course, if we have this, the question is, how can we detect it? And here, actually, I would like to put forward a very simple way, which I think is quite practical, because what we can do, and we actually also did some measurements in this direction in the experiment, is that we can not only look at the coherent forward scattering that was talked about so far mostly, but we can also look at the incoherent scattering to the side. And the basic idea is that, of course, the coherent scattering mostly depends on the dipole moment that we induce in the nuclei, whereas the incoherent scattering sort of relates to the population of the nuclei. So it's different density matrix elements. And if you now think about a situation, and I have just illustrated here for the simplest case of a two-level system that we just excite, I mean, the omega is the pulse area here, just barely beyond the linear response, and I've just expanded this typical Rabi oscillation here, then you can actually show, and this generalizes to more complex settings like many particles, even to some extent with interaction, that if you are in this linear regime, then the dipole moment squared, which sort of corresponds to the coherent scattering, is more or less equivalent to the population. And so if you have the ratio of these two light signals, it will just remain constant. However, if you go slightly beyond this, then this third order and the coherence comes into play as the next leading case, and this will give you deviations from this. And so if you just compare these two intensities in the experiment as a function of the number of photons in the pulse, which you can measure, then this may be a signature which allows you to detect actually this measurement beyond the linear regime in a rather straightforward way. And what is interesting is that actually works particularly well for multipulse control schemes. I didn't talk about it. It's this paper I mentioned in the beginning where we measured this time sequence, this time stability, because if you have the multipulse control schemes, then this argument works even better, and you get a really nice time-dependent ratio between the incoherent and the coherent scattering. Well, and then finally, if we maybe at some point really go to this regime where we maybe can think about inversion of the nuclei, then this may not be the best signature, but there's another one which we actually proposed quite a while ago, and I just want to mention it now maybe as the final thing. And that is that we can, again, maybe detect this inversion nicely in the spectral regime. And the reason is that the signatures we see now in the spectra, and also this Lamb shift spectra that Ralph showed, they are actually arising from an interference of the initial X-ray pulse that comes through and the scattered light of the nuclei. And if you now are in the low excitation regime, what happens is that there is actually, due to the scattering, an effective minus sign between the through-going light and the scattered light. And this then leads to an absorption feature in the spectrum. That's a typical absorption line that you see is due to this destructive interference. And if you go slightly detuned, you get a Fano line shape, which has a certain symmetry in there. But what you can now easily show, of course, is that if you go to a situation where you reach the inversion, then actually at this point, the dipole moment flips the sign. And that means that you can detect this point very easily in the spectrum, because now all of a sudden the absorption line actually turns into a gain line to some extent. And also at off-resonant condition, this Fano line shape actually flips the spectrum. And that's actually quite a robust signature, which even if now you have some problematic experimental condition, may allow you to actually clearly detect the point where you actually reach this excitation. And so this is maybe another reason why these studies in the energy domain will actually be the promising ones for the future experiments with nuclei at stronger excitation. Okay, and with this, I would like to come to the summary. So I hope I could also contribute to this message today that the X-ray free electron lasers offer really entirely new possibilities for Mössbauer science due to the higher spectral flux. And for the average spectral flux, we can talk about extreme transitions like the scandium-45, which was recently resonantly excited for the first time. And then I talked about possibilities with a high peak spectral flux related to this experiment with iron-57, where we now explored the energy domain under multiphoton excitation conditions. And then I showed you some theory results that actually with focusing and dedicated cavity design, it may be possible to go also in this strong excitation regime, and that we may be able to detect it then by looking at the ratio of coherent and incoherent scattering, or at higher extensity, maybe even at sign flips in the spectra. And with this, I would like to thank you, and I look forward to your talk, to your questions.
Yeah, thank you very much for this very interesting presentation. And of course, it's now open and prone to discussion and questions. Please, yeah. Ralph is clapping. That's not a question. Anybody wants to speak up? Yes, please.
Let me ask a general question. It's very interesting scheme you suggested to focus this X-ray radiation and to excite, but basically you need to excite the eigen waveguide modes, which you have in your waveguide. Mm-hmm. But if you focus too much, you are exciting mostly the evanescent modes, and that results in the bright spots you show.
Yes.
But there is an optimal way to excite, and you can also make it a kind of timing or duration of the pulse will allow you to focus, in a sense, through the excitation of the waveguide modes.
Yes.
So I see that this is really maybe a way to see really at least a small nonlinearity due to this population inversion.
Yes.
So did you study this? Did you analyze these evanescent modes? You are excited by your focus in light. This is the question.
What we do is, and I fully agree with you that this is the approach you suggest. So what we do is we calculate the mode structure of the cavity, and then we sort of project the free space Gaussian beam structure onto this, and thereby we calculate the field distribution. And for the moment, we now focused on situations where the nuclei are inside a structure, but in fact, we have some other work on cavity optimization, which is not in this high intensity limit. And there actually, as a somewhat unexpected result, you find that sometimes it's actually better to not have a cavity, but just a surface, and then maybe have these evanescent parts that you mentioned there. And I believe that this may also be the case here. We have not specifically analyzed it under the strong excitation, and also this temporal aspect needs some more attention from our side, I guess, but we have the tools because we now have really the expansion of the field in the cavity modes, and we can analyze it. Yeah, but it's in preparation, and we are still thinking about the best way to optimize it. And these evanescent ones, I think they are clearly also a candidate which might be very interesting.
Okay, thank you for this answer. And actually, just I can comment also one comment. Why you call this cavity modes while you have just waveguide modes?
Yeah, okay. I agree that it's sort of a waveguide. It's a planar waveguide, but somehow in the field, this cavity and waveguide is used interchangeably. And I think the reason is for most of the physics that we observe, actually the translation in the parallel plane is sort of neglected, so to say, that you look always at the 1D scattering geometry and then it appears like a 1D cavity. But I mean, waveguide, I guess, is the more appropriate wording.
Yes, I see. You are looking for the transverse waveguide modes. Thank you.
Yes, exactly. Yeah, yeah.
Okay, then a last short question by Olga.
Well, it's along the same lines. First of all, it's very interesting results and quite exciting, lot of ideas. But is it possible somehow to have a kind of optimistic estimate? So what, with your focusing and proper mode excitation, how many photons per pulse with respect to the number of nuclei you excite you could achieve?
Yeah, well, I hesitate a bit to give now concrete numbers because it's in preparation. But what I can tell you is the following. If we neglect the problem that, of course, if we focus stronger, we may face the problem that we just destroy the cavity. If we neglect these practical issues, then we can take parameters as they are delivered by XFEL and can assume focusing that has been demonstrated. I mean, you even find focusing down to 5 nanometers, which is then a dedicated experiment, but in principle, it's possible. And if you assume this and then calculate the excitation of the nuclei, so the insight there is that, of course, the dynamics of the nuclei ensemble as a whole is very complicated. But if you only look at the excitation phase, that's so quick that all the couplings and so on between the nuclei does not play a role. So they are, in essence, independent two-level atoms. One can also show this a bit in theory. Then you come in a regime where with these parameters, you can hope that you approach full inversion for actually a variety of isotopes that we tried. Yeah, whether really get this 100% and so on, I don't want to put my hand in the fire and so on, but you can clearly go in the strongly nonlinear regime with these parameters according to our current calculations.
Including iron 57?
Including iron 57, yes.
Good.
But I stress neglecting practical issues like cavity destruction if you focus too much. Yeah, I mean, this remains just to be seen. Yeah, yeah.
Okay, thank you.
Welcome.
Okay. Then I think with that, let's thank Jorgevas again for the presentation and move ahead in the program. Now coming to a presentation given by Joachim von Zantier from the University of Erlangen-Nuremberg, and he will present us collective photon emission of correlated atoms in free space.
Okay, so thank you very much. I hope, is it correct that is it the right mode?
It's fine. We hear you and we see the slide. Perfect.
Okay, probably I have to invert. Is it the right, is it this better? I think this is better, huh? The presentation now?
No? Now we see the presentation mode.
Okay, okay, so sorry, I do it again. Oh, sorry. On my screen it was inverted, but now it was better for you, so I do it the same way as it has been before. So this is okay, yeah?
That is okay, great.
Perfect. Yeah. Okay, so thank you very much. First of all, Olga in particular, for giving me the occasion to talk at this wonderful conference, which I really regret, of course, that we don't meet in person. It would be wonderful if we could do that in the future, and I'm very much looking forward. But at least I take the occasion to present here, and thanks for this, to present the recent work. I should first say that I'm really somehow misplaced, I would say, in this here now particular collection of speakers, because most of them before at least have been talking about the X-ray domain. But on the other hand, I would say I fit very nicely, I would say, because now according to the questions which have been raised, maybe I can give a few answers. And in particular, these wonderful questions asked by Vitaly. So what is a cavity putting in or modifying? And in particular, how are nonlinearities come into play? Even if you don't have probably enough photons. I would speak here about a particular situation where we only have 2 excitations and detect 2 photons, we leave the linear regime in that sense, but where we can see that a single photon really makes a difference. Just measuring one more photon than a single one, the single one would be the linear regime, but we have 2 excitations here, and we can see how a single measurement of a single photon really modifies the complete emission behavior of the second photon. So I think in that respect, even though I talk about the optical domain, I could nicely fit, and I hope at least I will do so. So the title is Collective Photon Emission of Correlated Atoms in Free Space, or it could also, the title could be How a Single Photon Modifies Dramatically the Emission Behavior of two atoms in free space. Okay, so I will talk about this in 3 parts. So I will very roughly talk about this collective photon emission of correlated atoms. And this brings us to the ideas which Ralph put forward already in his talk about super and subradiance. And I will show very briefly how this comes into play in this particular setup I'm discussing. And then I will talk about, why it is the modification comes into play, because we measure higher correlations, not a single photon, but 2 photons, 2 photon correlations, here in particular, not in time, but in space. And I will present some experimental results with single trapped ions in the optical domain. But this could be, I think, somehow linked nicely to also the X-ray regime, because the physics behind it is the same or are very much familiar. So what is superradiance? Of course, many people will know what this is. In free space, we have a single atom emitting isotropically and in time like an exponential decay. But this is strongly modified, of course, if we have a collection of atoms emitting, well, all of them stored in a small volume, so that if all of them are excited, a condition which Jörg just mentioned, I mean, a prerequisite that all of the atoms are excited, as will be the case, I will discuss later on in the case of 2 atoms, and we do not know where the photon, the first photon which has been emitted, comes from. This can be, for example, the situation if they are all in a very small volume here. Then, of course, we enter, even though initially starting from the fully excited non-correlated state, we would enter into the level of decay states, the ladder of decay states, where the single detection of the first photon would lead to a situation where 1 atom is in the ground state, but we do not know which of them. The second photon is detected, then 2 atoms are in the ground state, but we do not know which of them. And of course, these states which we produce in this way by measurement are highly entangled. This is a ladder of decay states, and we know also the behavior. This has been discussed by Dicke almost 70 years ago. The behavior is then completely different in time. It is a peaked behavior, a peak of emission, and even sometimes a directional emission, which scales with n squared, which is the reason why he called this spontaneous emission of coherent radiation at the time. I mean, this was the title of his paper in 1954. And he was really puzzled by the effect, even though the emission was spontaneous emission, as Jörg was investigating in the rectangular position, completely incoherent spontaneous emission. It behaved like a coherent emission because it scales with n squared. And that was a big puzzle of his paper and has occupied since many, many papers in the community, hundreds of papers written, of course. Now, I point out that, I mean, we cannot refer this back to a synchronization of dipoles oscillating a phase. I mean, a big discussion in the community since long, because each of these states, of these Dicke states, have no dipole moment. I mean, it is not the idea of synchronized dipoles, which is laying behind this n squared law. And so one can ask oneself, where does it come from that we nevertheless reach this n squared law, even though the emission is completely incoherent? And the answer to this is that we can observe Dicke super and subradiance due to the fact that the atoms are correlated. That is, the emitted light, the intensity depends on the initial state, whether we are talking about correlated or in particular entangled states, which were producing the light, or not entangled states. And to make that clear, we can have a look at the 2 different situations where on the one hand, we investigate a separable state, which is not entangled, and compare this situation with an entangled Dicke state. Now we start with a separable state of a double excitation, 2 atoms here, and both are excited and they emit 1 photon. Of course, this could be the situation that the first atom emits a photon or the second photon emits a photon. They both accumulate a particular phase when the photon is propagating from the atom towards the detector in the first case, and a different phase if the photon is emitted from the second photon recorded at the detector at the particular position. These are two different phases, but the final states are completely orthogonal. So if we calculate the total probability of measuring the intensity, then we would have an incoherent superposition of these two options because no interference is occurring due to the fact that these two final states are completely orthogonal. Now, if we consider the same situation of two excitations, but in a Dicke state, that is, we add a third atom in the ground state, no additional excitation, still two atoms excited, but we do not know which one. This is a Dicke state, a highly entangled Dicke state. Then we can look term by term for the same situation that two atoms are excited, but we do not know which one. If the first two atoms are excited, it's exactly the situation I just referred to. So we can add up either the first atom emits a photon, is accumulating a certain phase, or the second atom is emitting the photon, accumulating a certain phase. But the final states are again completely orthogonal. So the same is true for the second term, that where either the first or the third atom emits a photon is accumulating a particular phase, but again, the final states are completely orthogonal. And the same is true for the third term here, where the two last atoms are excited, emit a photon, accumulate a certain phase, and the final states are completely orthogonal. But due to the fact that we talk about the entire state, which is entangled due to these coherences occurring with these plus signs over here, we can find that we have final states which indeed give rise to interference. These two over here, these two over here, these two over here. And that makes a distinction towards the transparency, which I showed on the slide before, the situation I showed on the slide before. Now we have final states which may give rise to interference effect, and we end up in a different result with respect to the transparency before, that the total intensity is increased. So if we then do the full calculation, we investigate the number of final states, how many terms lead to the final states. In the situation on the transparency before, I had 3 different final states. To each final states, there were 2 terms, 2 quantum passes which contribute to these final states. I take the normalization into account and I calculate the total intensity. I end up in a very, very simple formula where NE stands for the number of the atoms in the excited state, NG stands for the number of atoms in the ground state. But of course, I do not know which ones are excited and which ones in the ground state, which is exactly the formula by Dicke derived almost 70 years ago, and which, for the case that half of the atoms are in the ground state and half of the atoms are in the excited state, lead to the famous n-squared law. So this shows that this superradiant effect, I mean, of which Dicke was talking about 70 years ago, really stems not from a synchronization of dipole, but stems from the fact that we are talking about entanglement, entangled states. Now, I mean, this is a very short recapitulation. Now, if we look not only for the maximum intensity, which I was discussing so far, but take also the phases into account, which I discussed on 2 slides or 3 slides before, the phi1 and the phi2 and the phi3, I can really see that for a configuration where I have here all the atoms along on a linear array, I have a focused emission of radiation in the forward direction, in this forward direction over here, even though the emission is completely incoherent. It's spontaneous emission, it's incoherent. And for the same argument, I can also explain non-symmetric Dicke states, I mean, so-called non-symmetric Dicke states, where I have in the forward direction with the same argument, what we call subradiant. I'm speaking now not in the temporal domain, I'm speaking in the spatial domain of superradiance, directional emission of radiation, of spontaneous radiation in the forward direction. This is superradiance, or decreased emission in the forward direction, which I call directional subradiance. All linked to the ideas of Dicke of his paper in 1955. Okay, having put this down, now the question is how we can produce these super and subradiant Dicke states. And this is usually very, very complicated. But there's one technique which we can exploit, which goes back to the ideas of Henry Brown and LPHYS', where we measure at particular positions in space photons, so that when we start from the fully excited state, we can produce these symmetric or non-symmetric Dicke states. So the idea goes back to the original ideas of Henry Brown and LPHYS', of course, measuring incoherent light from 2 stars with 2 detectors. We go down now into the microscopic domain, where we have, for example, 2 atoms and 2 detectors, and we use one of the detectors to produce such a kind of decay state, and then measure the intensity distribution of the decay state such produced. And this can be generalized, of course, I mean, even to N emitters and M detectors, but I will not go too much into this direction because I want to discuss right away the situation which we realized in the experiment where we had 2 atoms here, not interacting at all, and have 2 detectors. So very much the Hanbury-Brown twist measurement, the original Hanbury-Brown twist measurement. And you can see if I start from the fully excited state, so this is the reason why it is so important, as Jörg discussed, that we go into the fully excited state. So if I measure 1 photon in the far field and I do not know where this photon comes from, I will produce a decay state among these atoms which do not know of each other. Because I do not know whether the first atom or the second atom has been put into the ground state, including a relative phase between these options shown here in brown. So this produces a configuration of a decay state with a detection of the first photon. And then I use a second detector to investigate the superradiance or subradiance of this state, which I produced with the second detector. So I measure the first order correlation, that is the intensity of the decay state over here. And if I do the calculation in theory, I end up with such a sinusoidal oscillation, which is completely coincident with the decay formula where I have 1 atom in the excited state and 1 atom in the ground state. So this gives me a maximum of intensity of 2. As I can see here, the maximum intensity is 2. So this is a super radiant behavior. But at the same time, I measure the second order correlation function, of course, because this is a configuration of Hanbury-Brown twist. And so this shows that the Hanbury-Brown twist measurement and the super radiance is completely the same effect, just looked from a different perspective. Now, we can generalize this, but again, I will not go into too much detail of this. I can have, of course, N emitters and M detectors. And if I start from the fully excited state and I measure 1 photon, then I will end up in a decay state with 1 atom in the ground state and the rest of the atoms in the excited state, but I do not know which atom is in the ground state. If I measure the second photon, then I have 2 atoms in the ground state and the rest of the atoms in the excited state, I do not know in which state I am. And of course, after M measurements, I will measure the intensity of a decay state with M-1 atoms in the ground state, the rest of the atoms in the excited state, the highly entangled decay state. And this is, of course, the same as the M's order correlation function of the fully excited state, which, if I do the calculation, again, gives me an incoherent sum of the different final states I can obtain, including the different quantum passes to a particular given final state. And I do the calculation, and this can be give very interesting effects. I will not talk too much. Instead, I would like to go to the experimental result we did with 2 single trapped ions. So very much the situation I discussed in theory before. The only difference is that we are now not in a pulsed excitation. Both atoms are in the excited state, but they are laser driven. It's not such a big difference, though. Again, I have here this, if you remember, this 1 plus cosine result, which I obtained in the case of 2 atoms in the excited state. Now they are laser driven, so it depends how strongly I drive them according to the saturation parameter over here. But the essential result is obtained in the same way as if they would be in the fully excited state, namely this modulation or interference effect with a visibility of 100%. And now remember, the detection of the first photon projects me into different decay states, depending on the phase here. And that depends where I put the first detector. And if I put it in a symmetric manner, as is shown over here, I will produce a symmetric decay state, where now I obtain such a cosine modulation as is shown over here. And if I do the calculation, I can see here this super radiant behavior in the forward direction I discussed beforehand. So in the forward direction, I have a maximum. But I could also place the first detector in the situation where I have an antisymmetric situation, where the phase here, if you compare this phase over here, gives me a minus sign over here. Minus sign, so I produce a fully antisymmetric state, in which case I get a situation where I have what I call subradiant behavior in the forward direction. So it really depends on the detection of this single photon over here at a particular position in space, where the complete behavior, emission behavior, is completely modified. So we did this measurement. We realized this in the laboratory of Ferdinand Schmidt-Kahler in Mainz, where he was able to trap 2 calcium atoms at very far apart, a couple of micrometers, so they do not interact. And we do the measurement using a camera where we place the two cameras spatial resolving, and with a very high time resolution of 50 picoseconds. I should say the lifetime of the state is 7 nanoseconds. The time resolution of the camera is 50 picoseconds. So easily we can detect coincidentally or as a function of time difference in the coherence time, that is the upper lifetime of the state. And so the only drawback of the camera is that it is dead if one photon hits the camera. That is the reason why we have to work with 2 cameras to realize a spatial Hanbury-Brown twist experiment, as I will show in the next transparencies. Now, this is the result. Now, this stepped line here is a position of my pixel of the first camera over here. And so this is the XL distribution of the second camera over here. So I have the spatial behavior as a function of where I detect the first photon on this camera over here. And here I have the time relative time behavior in time and tau in nanoseconds, which I can easily resolve. Now I go back, I remind you of the 2 situations: super-radiant behavior if I detect with the first photon in a symmetric way, sub-radiant behavior in the forward direction if I detect with the first photon in a so-called non-symmetric decay channel, I mean on a non-symmetric situation. So this is what is expected by theory, and this is what we obtain in the experiment. If we measure in a symmetric configuration, we have indeed in the forward direction super-radiant behavior. If we measure in a non-symmetric, the first photon in a non-symmetric way, we have in the forward a so-called sub-radiant directional behavior. So now, of course, we can put our detectors anywhere in between, and instead of only having sub-radiance or super-radiance, we could have anything in between. But it really shows, and that is my essential point, that the detection of a single photon makes a difference, because it brings via projection the entire system, and that could not be only 2 atoms, but it could be n atoms in an entangled state where the emission behavior is completely modified. It's not a linear behavior, it's highly nonlinear, but it does not require a lot of intensity, a lot of photons. It's a single photon which makes a difference. So this is more or less my last slide. I just want to say that if you measure second-order correlations, 2 photon correlations, we can have a complete different behavior, high oscillation behavior. If I would measure only 1 photon in this, starting from the fully excited state, I would have an isotropic intensity, no information at all. So this brings me to the conclusion. So I pointed out that spontaneously emitting atoms, completely incoherent light emission in entangled decay states emit super and subradiant light, spatially dependent in the forward direction. And we understood superradiance as a consequence of single photon quantum paths constructively interfering in case of initial decay states. And so we realized that we can produce these decay states from completely uncorrelated atoms, all in the excited states, by generalized Hanbury-Brown twist measurements, which again shows that Hanbury-Brown twist measurements and superradiance are 2 sides of the same coin. They're closely linked to each other. And with this, I should say, of course, I did not do this alone. Of course, this is a long-standing collaboration, of course, in principle, also with Ralph, and of course, in principle, also with Jörg. But in this particular case, it was Ferdinand Schmidt-Kahler, because we were working in the optical domain, Girish Agarwal, of long-standing collaboration. But I would like to highlight my PhD, Stefan Richter, who did all this work. If you go into the details, these are many, many days of measurements, even weeks of measurement in a stable ion trap, so very complicated. And with this, I close and thank for your attention. And I'm open, happy for questions, of course. Thank you.
Yeah, thank you very much for sharing this intriguing insights. It's now open for questions. Yes, Vitaly?
I would like to briefly comment that, in fact, description via the decay states and via the electrodynamical approach are equivalent, and the radiation you mentioned could be of superradiance. Superradiance is the radiation of coherent dipoles, even when they start from the incoherent, fully excited states. And the point is that in the example you have to consider the modes of this sample, and some modes in inverted medium becomes unstable, and each mode obeys the Bose statistics, and these quantum fluctuations produce this initial level of intensity of this mode, which then exponentially increases in time, and then they produce this super radiance. So there is no any contradiction between two descriptions. Description by Dicke states is more simple and appropriate for the sample with less wavelength sizes or point-like atoms, and for the extended samples, the electrodynamic description of the modes of this cavity or whatever open cavity is more efficient in a sense. So no contradiction. This is what I would like to stress.
Okay, thanks, Vitaly. I would strongly disagree, and probably we have a longer discussion on that, because you have, in your description, I would not see how entanglement comes into the play. You see, if you have the synchronized dipoles, this is a dipole and electron classical approach, but which would not be able to display any entanglement or correlations in time. I did not show it. I mean, you have anti-bunching behavior. You have bunching behavior of this crystal. I did not talk about this, which you would not be able to derive in a classical description as you propose.
No, not classical, quantum description. You should have to quantize these modes, and then you will have all this entanglement and quantum statistics involved automatically, but from a different perspective.
Yes, but your mean dipole moment is non-zero, I believe. Is that correct?
The dipole mode of transition of atoms, of course, they have to emit some radiation. Otherwise, there would be no spontaneous emission at all.
Yes.
But
and that
I'm afraid that we have no time. We have 10 minutes left, and we have one more talk in front of the next session. Maybe if you still be able to join, maybe by the end of the next session. Otherwise, we have no time. I'm sorry.
Sure.
Also, Ralph's question should be then probably put forward in
yes.
So let's come to the last. Thanks again for the presentation, of course, and come to the next and last one.
Yeah, thank you so much.
Which is by Shiwen Zheng from Texas A&M, presenting in a 15-minute presentation, nuclear quantum memory for hard X-ray photons.
Shiwen, try to be as short as possible.
Where's my...
We see a slide, but we don't hear you.
Where's my Zoom? Here. Yeah.
Okay, we see you and we hear you.
Okay. Now PowerPoint.
Okay, go ahead. It's fine.
Is it working?
Yeah.
Yeah, okay. So I'll try, but I'm not sure. Yeah, let's see where it ends. First let me thank Olga for letting me talk about the experiment work on nuclear quantum memory for hard X-ray photons. And this work has been done in collaboration with amazing groups from Daisy from Texas A&M, Jena and ESRF. So over the past decade, there has been rapid development of quantum computer and quantum communication. Time-being qubit is one of the most robust flying qubit, and the quantum memory is the essential element for quantum information. To store such time-being qubit, we need to store not just the photon number, but also the temporal wave packet in the medium. In the past, there have been two types of quantum memory schemes for single photon waveform. The first is EIT and Raman, which mapping single photon wave packet into the long-lived spin wave in the medium, either by modulating the control, the amplitude or refractive index or propagation direction of the strong control field. So at the minimum, this scheme requires the existence of both three-level system and a strong laser. For a two-level system, one can do so by a photon echo technique, which can be implemented in two ways. The first, the gradient echo memory, where we have a very narrow transition line width, and then external electric or magnetic gradient field is applied to the medium to induce artificial inhomogeneous broadening. Upon photon absorption, the D phase of the polarization field due to the artificial inhomogeneous browning prohibits the re-emission. So until the external field is reversed, which corresponds to a redoubt operation. The atomic frequency comp, on the other hand, start from very broad inhomogeneous browsing, and then a discrete absorption structure is burned onto this profile by spectral tailoring. So due to the beating of the polarization wave, echo is generated periodically. So all these techniques are designed for the application in optical regime. It is of great interest to extend the concept of quantum memory to the hard X-ray frequency range, but it's not so straightforward because traditional protocols don't work well in the hard X-ray regime. There is no strong laser and no natural three-level system, so EIT and Raman are not possible. There is no broad inhomogeneous browning, no laser for spectral shaping, so atomic frequency comp is not possible. Because Bohr magneton is so small, the implementation of gradient echo memory requires tens of faster switching, tens of Tesla faster switching magnetic field. The solution we suggest is to use several identical Mossbauer targets, each moving at different velocities. Due to the Doppler effect, the frequency comp, this form of frequency comp in the absorption spectrum, so we call it Doppler frequency comp because it's implemented in a nuclear system. We also call it a nuclear frequency comp. So unlike atomic frequency comp, these comp teeth are distributed along the way of photon propagation direction. So we don't need a large inhomogeneous browning or a strong laser or accelerate levels for spectral shaping. And we don't need a strong magnetic field either because the gradient is already naturally present in the system. So this protocol should be very suitable for hard X-ray quantum memory. As an example, if we take 557 targets, each with optical thickness 12 and moving at velocity spacing 0.9 millimeter per second, then the input field of intensity duration 16 nanosecond can be stored in this example for 96 nanosecond. Of course, experimentally, for the initial investigation, instead of building a new source running 10 nanosecond duration photon, it would be much more convenient to just use synchrotron radiation. However, this is 2 to 3 orders of magnitude shorter in duration than in this example. So we need to keep this in mind always, that there's a mismatch of bandwidth when we try to demonstrate quantum memory. So here's the illustration of the experimental setup conducted in DAISY and the ESRF. We have 7 iron-57 enriched stainless steel foils mounted on 6 Mossbauer drives, oscillating slowly at frequency 27 Hz, driven by a master signal. Because the input pulse has so short duration that within one oscillation period, we have a well-defined yet different frequency comp at every instant of time. And the input, the average photon number per pulse of the incident field is 0.01. So the experiment is conducted at a single photon level, and the collective excitation of the nuclear ensemble carries maximum 1 quanta. This is an example of the experimental result. If we move the sample at velocity spacing 3.48 millimeter per second, we should expect to see echo at 25 nanoseconds, and indeed that's what we observe. If the targets don't move, then a much weaker signal is observed due to the usual Bessel type of dynamical beating. Here's an accumulated two-dimensional histogram of the experimental result. As expected, the larger the velocity spacing, the smaller the echo refacing time, and there's no echo if the targets don't move. we also see the pattern of dynamical beating on top of these echoes. If the finesse is smaller than the optical thickness of each target, which is 29 in our experiment, then the echo gets smaller, get weaker and weaker because of the higher order reabsorption processes. The strong refacing of the emitted photon by nuclear frequency comp can be seen more pronounced in this by directly comparing 4 different velocities. In this particular case, if the targets don't move, then the remission follows follows the superradiant decay of a 22 micron thick stainless steel with dynamic beating clearly seen in this inset. For nuclear frequency comp, on the other hand, the remission is strongly reshaped into a repetitive structure with dramatic enhanced emission probability at those refacing time and decreased in between. Therefore, we have experimentally realized the hard X-ray photon echo by nuclear frequency comp using a synchrotron source. So we're in a good position to go ahead to try to see the quantum memory feature of this setup. In order to verify the quantum memory functionality, we need to observe the waveform preservation of the X-ray photon echo. Therefore, we need to reduce the bandwidth of the incident hard X-rays, and we do so by adding a thin film cavity to trim down the bandwidth. The waveform of the cavity is more or less exponential decay. So in this part of the experiment, we are specifically looking for the evidence of exponential trailing tail of the X-ray photon echoes. Without the cavity, this is what we see. And with the cavity, clearly we see that the photon echo carries the exponential falling edge. And this waveform preservation is totally due to the presence of the nuclear frequency comp, because if the target don't move, then the emitted photon will not carry this exponential falling tail. So this slice is a cut of the 2D histogram of 3.1 millimeter per second velocity spacing, and the cavity decay is overlaid on top of this first echo. And clearly, the exponential falling edge is very well recovered by the first echo, but the stepwise rising edge is not well recovered because this sharp rise cannot be stored by a finite bandwidth quantum memory, and this is a major source of the degradation of the fidelity. So quantum memory efficiency is defined by the number of input photon divided by the incident photon, but the incident photon is not experimentally accessible. It is convenient to introduce echo efficiency, which is just the number of photon in the echo divided by the number of photon in all echoes. It is just a function of optical thickness and velocity spacing. Essentially, it takes into account all the coherent losses. Namely, you need to choose the loss either into the non-interacting instantaneous transmission channel or the loss into higher order echoes. And it is this balance of the two channels that give the upper bound of the 54% efficiency. The total number of input photon can be fetched by considering the incoherent and inelastic loss channels, including electronic scattering, such as photoelectric absorption, Compton scattering, and nuclear incoherent scattering, such as nuclear fluorescence, and so on. The finesse is defined with respect to the intensity rather than the field, because experimentally the phase information is not accessible. With that, we see that the echo efficiency peak at 33% at velocity spacing 3.1 millimeter per second. It decreases for smaller velocity spacing because photons get scattered into higher echoes due to the strong reabsorption and re-emission processes. It decreases for larger velocity spacing because photons, in this case, tend to transmit without resonant interaction because the absorption is simply too weak. after considering the incoherent losses channels, which in total give a 75% loss, the final quantum memory efficiency in the case of 3.1 millimeter per second is 8%, and the fidelity is 67%. The fidelity increase with velocity spacing until saturation. For smaller velocity spacing, the Cohn bandwidth is simply too narrow to recover the waveform of the cavity decay. And for larger velocity spacing, we don't have enough data because the echo period becomes too short. So we also investigate the influence of the robustness of random deviation of velocities and the thicknesses. We see that this protocol is robust enough for quantum memory. In conclusion, we demonstrate quantum memories for 14.4 keV hard X-ray photons for efficiency 8% and fidelity 67%. This is a tunable, robust, and highly flexible system, which offers a promising platform for compact solid-state room temperature quantum memory in the hard X-ray regime. Thank you.
Yeah, thank you very much also for keeping the time. There's, I would say, one more time for a short question. I don't see any. So then everything was clear, and I think we can then thank you as the last presenter, thank all the speakers of this session, and by that excuse also to the following session for the delay, and close it and switch over to the program.
Thank you so much, Peter. Thank you. We have no time for break, and so I suggest that we just continue. And so, John, are you here?
Recording stopped.
Yes, I'm here.
Recording in progress.
Maybe we should take just like a 5-minute break or something. Would that be useful?
Okay, let's take 5 minutes break.